What today is like introduction to transform. Mostly I'll be discussing you about the Laplace transform. Okay. If you see the previous chapters, so far we covered in the chapter 1 matrix and determinants. In the chapter 2, we have talked about the differential equations and how to solve a differential equation for a first order and second order differential equation. Solution method has been discussed. And in third chapter we saw vector calculus and what is the difference between that vector variables, like what is the curl, divergence, and gradients. All these things has been taught in the third chapter, and the integration of a integration of a vector function. So the practical things has been taught in the third chapter. In the last chapter, complex functions and variables, complex variables and functions. We thought about. I introduced you something like complex functions, and we have seen where the derivative of a complex function exists, and integration of a complex function using Cauchy integral theorem. All the things has been taught in the previous chapter. So far we have covered 4 chapters. This is our 5th chapter. Okay. So people who has to enroll for the course, you can see the for enrolled students, all the previous videos is available in the website. You can go and see the videos. Okay. Then Laplace transform. So Laplace transform, in a sense, transform. The advantage of as usual, like people who are attending my class, first initially let me focus majorly on exam point of view. If the time permits, means I will tell you that I will take some bonus points. Okay, so the bonus lecture. So usually for Laplace transform, you need to connect Laplace transform with Z transform and Fourier. So it's better I'll teach you the Laplace transform, the solution methods first. Then in the last lecture of the chapter, I will give you the practical idea. Okay, how it evolved. What is the background behind this, the reason behind this Laplace transform and all. Okay, first mainly we'll focus on exam point of view. Okay, Laplace transform. A transform, in a sense, we are transforming like a function from one domain into another domain. Okay, for example, Laplace transform is used to transform a time domain. Okay, a time domain, if you transform this function, okay, it transforms the time domain into a frequency domain. Practically speaking, it transforms a time domain in a real value function to a frequency domain in a complex function. Okay, but I will teach you that time permits, means I will teach you the reasons why it is going to the complex function. Okay, and all the things. But as of now, we'll focus mainly on exam point of view. Okay, so it transforms a time domain into a frequency domain, Laplace transform. Okay, so the Laplace transform of a particular function f of t is nothing but Laplace transform 0 to infinity f of t into e power minus st into dt. Okay, if you see that this integral are nothing but indefinite integral. You see that for definite integral means we can say that like first thing is definition of integral in the limits. If it doesn't have any limits, means it is improper integral. Okay, proper integral means they have to give the limits. You got it right? It is improper. A limit, a function without any limits is nothing but improper integral. A proper limit means it should contain a limit a to b. It's a proper integral. Even in the proper integral, there are 2 types. One is like definite, and another one is indefinite. A definite means like a finite value. For example, integration of minus 10 to plus 10, f of x dx. See, this is a finite value, right? The 10 is finite value. But indefinite integral means integration from minus infinity to plus infinity, f of x dx. Okay, infinity to infinity. Infinity is something like, it's uncountable. You got it right? So it's kind of indefinite integral. You are not giving the proper limits to me. Though it is given the limits, it is indefinite. Okay, it's indefinite integral. You got it right? So the Laplace transform, we see the limits. The limits are indefinite integral. Okay, 0 to infinity f of t into e power minus st into dt. You got it right? So this is a conversion of a function into a Laplace function. So Laplace of f of t is nothing but 0 to infinity f of t into e power minus st into dt. If you see the limits are unilateral function. It is from 0 to infinity. Okay, suppose for bilateral function, if you want to transform, there are like this is the authentic definition of Laplace. Okay, there are some other functions as well. Bilateral transformation. For that, the limit is minus infinity to plus infinity. f of t into e power minus ft into dt. Okay, but everywhere in your syllabus you'll be focusing mainly on this thing only, guys. Okay, this is what the proper definition of Laplace transform. It's a unilateral 0 to infinity f of t into e power minus st into dt. Okay, so let us try to solve the Laplace transform of some functions. If f of t is equal to 1, e power at and trigonometry function. So let us try to solve the Laplace transform of a constant function, then exponential function and trigonometry function. Okay. And the major reason while the Laplace transform evolved, right? The major reason for people they'll be using the Laplace transform is it converts a differential equation. Okay, if you take a Laplace transform differential equation, it converts the differential equation into algebraic solution. Okay, it converts the solution of differential equations, right? Anyway, I will be teaching you in the last part. Don't worry about that. Just take note of it. It converts a differential equation into algebraic form. Then you can obtain the solution in the algebraic form, right? In that particular domain. Suppose this is my function domain. So it took Laplace transform. Okay, this is Laplace domain. Okay, Laplace transform domain. Okay, here the solution of the differential equation is simply algebraic form. Okay, we can obtain a solution very easily because since it is algebraic form, we can obtain the solution very easily. Once you obtain the solution, just take the inverse back. Okay, Laplace, get the algebraic form, get the solution, then take the inverse back. So a solution of a differential equation which is very complicated in here can be easily solved in the Laplace domain. That is one of the potential application of Laplace transform. You got it, right? So suppose I am having differential equation. The solution of differential equation y dash y double dash can be get from take the Laplace, get the algebraic form, find the solution, and to take the inverse of the Laplace. Finally, we will obtain the solution. These are the solution steps. You got it, right? These are the one of the major application of Laplace transform. The other applications are like one is Heaviside function, other one is Dirac delta function. I'll teach you that once we are going into the